So let's look at the fundamental physics, the formulas that contain the fundamental physics. The first one is the Lorentz force law. The force is QE plus QV cross B. And the second one is the Faraday-Maxwell equation, where you have integration of the non-conservative electric field dotted into ds equals minus integration partial B by partial T dot dA. This is the form that it should be written in to be one of Maxwell's equations. And then you have the fundamental definition of the EMF, which is integration of F over Q dot ds over the contour that forms along the wire, closed loop. So these are the fundamental rules. And then we showed that the EMF, based on this definition, you can prove that the EMF is always equal to minus d phi by dt, magnetic flux with respect to time. And this is the case if the wires are fixed and the magnetic field is changing, or if the wires are moving and the magnetic field is constant, or both the wires are moving and the magnetic field is changing. It doesn't matter what the reason is, but always the EMF is minus d phi by dt. And this is the reason why in textbooks, usually in the freshman level textbooks, they only write this equation, because you don't need to think about each case independently. It always works no matter what happens. So if you want to solve a problem to get the EMF in any problem, doesn't matter what the problem is, you first get the magnetic flux, get d phi by dt. If you have more than one loop, multiply by the number of loops, and that will give you then the magnitude of the EMF. The sign is not really important. Then if you want to get the direction of the induced current, you use Lenz's law. So this is the map how to solve any problem to get the EMF and the direction of the current. Okay, now in the special case when the wires are not moving, we showed that the EMF in this case is only integration of E non-conservative dot ds. There's no part due to the magnetic force. And from the fundamental definition of Faraday-Maxwell equation, we showed that this part where the derivative with respect to time is inside the integration, it can be taken outside because the wires are not moving. So we discussed this before. So you can rewrite this as rate of change of magnetic flux. And so in this case, where the wires are not moving, then the EMF is integration of E dot ds, and it's minus d phi by dt. So this is the rule that you would use if you want to find the non-conservative electric field in a problem where you have a contour that's fixed in space, that's not moving in space. And there are many problems that fall under this category in the problem set or the homework. And then in the special case where the wires are moving but the magnetic field is constant, then we showed before that the EMF in that case is integration of V wire cross B dot ds, and still it's equal to minus d phi by dt. So this works for the case when the wires are moving but the magnetic field is constant.